start part B of Module 1, Power of Algorithms. In this part, I will use a simple example to show how powerful we can get if we use good algorithms. All right, so part B.1, evaluate the polynomials. So we start with a very simple problem. Our problem 1 for this class, evaluate a polynomial. First, it is a very simple problem because we know how to evaluate a polynomial, right? Yeah, because we have done that many, many times. Yeah, nobody even think about it. Yeah, because so simple. Yeah, but here actually you can have a lot of things to do in order to do an efficient evaluation. Yeah. First, let's take a look at the problem. Given a polynomial, p of x equals this standard polynomial format, then here we are given coefficients, a set of coefficients. Yeah. So we pass all the coefficients to our program as an array containing all the coefficients for this polynomial. So after that, then given a variable x, we can do the polynomial evaluation. Okay? All right, so now the question, how to evaluate p of x efficiently? So here, the main point is efficiently. I know you can evaluate it. So everyone can evaluate it correctly, right? So get a correct answer. But you may not evaluate it efficiently. Yeah. So in this part, B.1 and the remaining, we have a few more parts, we will try to find the best way to evaluate a polynomial. All right, so let us do some analysis. First, do we really need an algorithm here? Because it looks like so simple. Why you need some fancy algorithm, right? So first you may ask in like this. Yeah. So we will see the huge difference later. Yeah. All right, and we can observe a simple fact. Each polynomial evaluation contains two types of operations, addition and multiplications. Okay, so these two types of operations. Yeah, so very simple. Yeah. All right, so next, now the question, how to measure efficiency. Yeah, so we like to know how efficient it is, but the question is how to measure the efficiency, right? So there are many different ways to measure the efficiency. Now, the first way that most people can think of, so that is use the execution time. Yeah, so we clock it. So in our program, so we set, at the beginning of the evaluation, we get a current time. Yeah. At the end of the evaluation, we get another current time. Then we take the difference. So we can find the response time. Yeah. Evaluation response time. Is that a good measure? Right? Yeah. That measure useful, but it has its own problem. It has its own problem because it is very hard to compare two different algorithms using their response time. The reason is very simple. Do you run your program on a very powerful supercomputer or another person running the same program but on a very slow computer, 10 years old computer? Okay, still can get the correct answer, but can you compare the response time? Right? The same algorithm, right? One is much faster than the other one, but that difference is because of the hardware difference, not the algorithm difference, right? So this kind of measure, not very stable, right? Not very stable. So we want some stable, solid measure. Yeah. All right. And objective. Yeah. It does not depend on the machine. Yeah. It does not depend on, many other different factors. Yeah. All right. So to do that, we use another objective quantity to measure. All right, so using number of additions and multiplications. So that's another idea. Number of additions, number of multiplications. We do counting. Count how many additions, how many multiplications do we need to find the solution. If we get that counting number, it does not depend on your machine, right? So it is a better measure. So this one is a better measure, so we can compare two different algorithms. Then using this measure, we can get a pretty stable comparison. So all right, next, so we want to work on this question now. All right. The first try. When we solve a problem, we may need to try many, many times. So the first try, it may not be the best solution. We just want to get a solution first. Okay. So in our first try, we just use the straightforward algorithm, the way everyone knows how to do it. Right? The trivial one. Okay? Yeah. All right. So how to do it? So you can see we do it this way. Work on each term. And actually, when we work on each term, we count the number of multiplications. And here, we consider the general term. A sub k, the coefficient, times x to the kth power. How many multiplications do we need to evaluate this term? That's the basic step. Yeah. If we can do it, then we can do, evaluation for the whole polynomial. So that's simple. Okay. All right. So for the number of multiplications for this particular term, although it is pretty easy, but I want to delay it, later. Later we will really do the details. So at this point, you can think about it. The answer is pretty obvious. But we will delay just, a few more slides. All right, next. All right. So this part, this particular example, I put here as our problem number 1, the reference in our textbook, section 6.5, page 234. Here you can see I may not follow the natural order of the materials in our textbook. So based on my understanding, my way of presentation, so I may jump. Okay? Here, I want to show you the power of algorithms. So I feel this example is one of the best. So I select. So even it is in section 6.5, I like to use it right at this point. Okay? We have the sufficient knowledge to understand this algorithm. So don't worry. We can understand completely. All right, next. question with our current evaluation. Yeah. So the one, everyone can do it. Yeah. So the question is that one efficient? Right? Yeah. Is that a good solution? Right? So we need to ask this question. Okay? Because we want to know if we still need to improve upon this current solution, this solution. Yeah. If it is already the best solution, then we do not need to do anything, right? Yeah. But if it's not a good solution, we need to find a better solution. Yeah. But this question here, at this point, it is very hard to answer because we don't know other solutions, right? We only know this solution. We cannot do any comparison. Yeah. So next, we need to do, try to find a different solution and do the comparison. Okay, all right. So the question, are we satisfied with the solution? If we do not have any option, how can we answer this question, right? Yeah, so we need to have some options before we can answer these questions. Okay, yeah, all right, yeah. So at this point, we do not know how bad or how good is this algorithm. Okay, so we need to do more work. Okay, all right, so the next step, what should we do? Next step, yeah. So next step, find the performance number of this algorithm. Yeah, the number we already discussed, right? Number of additions and multiplications. That one we use as our performance number. Okay, so we can do objective comparison. Yeah. All right. Okay. So next, we need to get that number. Yeah. All right. So let's do analysis. Yeah. Yeah. When we try to find that number, okay, find that number. Yeah. Yeah. Find the number of operations, including additions and multiplications. Yeah. So we may need to do some assumptions. Yeah. Because the given problem does not give us much information. Yeah. So in order to get a better analysis, so we may like to add some reasonable assumptions. Yeah. All right, so here, yeah. So what do you mean the reasonable assumptions, right? Yeah. So here the assumptions we are going to add should not alter the original problem significantly. Okay? You should not change the original problem. Yeah. You can change, at some minor places, you can change a little bit. So it's okay. Yeah. But the, overall difficulty of the problem still the same. Then you solve the same problem, right? So here we do that. Yeah. We make some reasonable minor assumptions. All right. So let's take a look what kind of assumptions we make here. First, each addition takes 1 unit of time. So here you can see, so we try to associate some number to each addition operation. It's not given in the original problem, but we can assume some unit time. That's reasonable, okay, not too much. Second, each multiplication takes 10 units of time. Okay, yeah, another assumption. Yeah. So this one, we know, everyone knows multiplication is much slower than addition. But how much slower? Yeah. So usually that number is not fixed. Yeah. So that number can vary, up and down. Yeah. But this 10-to-1 ratio is a pretty reasonable one. So in the real world situation, it is close to this number. Not exactly this number, but pretty close to this number. So here we can, for the convenience, so another thing is for the convenience, we just make this assumption. 10 to 1 time ratio for these two operations. Yeah. You just get the idea, multiplication is much slower than addition. All right, yeah. Next, then we can do further analysis. Yeah. All right, so what unit we are talking about here, right? Yeah, what unit? Yeah. Certain number of nanoseconds. So in the real world, current technology, the CPU performance number, a regular computer, normal, regular, usual computer, to find the answer of one addition, it takes several. So usually it's a small number, 1 or 2. Okay, so 1 or 2 nanoseconds in that category. Okay, so pretty much in that category. But we don't need a precise number there. Okay, Here we know a nanosecond equals this second, 10 to the negative 9th second, or 1 billionth second. 1 billionth second. That's small. Okay? All right. So in this way, this kind of assumptions, in our discussion, we can make our situation, communication, much easier. Okay? So you can see we do not change the difficulty of this problem. Still, the same problem. We just add a little more details, reasonable details. So it is okay. All right. After that, next, we need to get a number, performance number, counting number. All right, so let's do it. All right, let's do the work. First, let's calculate the number of additions. So that's simple. So that's pretty simple. But even it is very simple, I'd like to talk about what method we use to get the right answer. So first you can try. Can you tell me how many additions do we need? Only additions. Do not look at the multiplications. How many additions do we need? Right? Some of you can get a quick answer. Okay? I believe it. All right, so let me give you my answer and my explanation and analysis. All right. Here, I want to talk about counting technique. This is a simple counting question. In your discrete math 3000, you learned the counting topic, right? There are some basic counting techniques. So I hope you have some idea about it. But here, let me talk about one particular counting technique we can use here. So it is called counting by reference. This method, counting by reference. We need some reference. When we do counting on some mathematical objects, sometimes we need to use some good reference to help us to get an answer. So let me explain this method. Very simple, but very effective. All right. The essence of this method, discover one-to-one correspondence. This is very important. Discover one-to-one correspondence between two mathematical objects. two mathematical objects, or we establish one-to-one correspondence between two mathematical objects that can help us do the counting. All right, so here let me describe the idea in this way. We have object 1, object 2, two mathematical objects. Here it's pretty abstract. Okay, so later in our example, I will tell you what is object 1, what is object 2 in our example. Here I just described the general idea first. Yeah. All right. For object 1 and object 2, we want to establish this one-to-one correspondence. Okay, one-to-one correspondence. All right. Then we can use it for counting. Because for object 1, usually it is hard to count. It is hard to count directly. Okay? Because the reason is it is hard to keep track of the object 1. Okay? But after we connect it to object 2, object 2 has the property it is easier to count. Right? So then we just count the number of object 2. That number is the same as the number of object 1. Why the same? Because this one-to-one correspondence. Right? One-to-one correspondence. So you count the number of one object, it is the same as you count the number of the other object. That's simple. Okay? Yeah. Now, back to this example. Now, let me explain one-to-one correspondence here. First, look at what is our goal. Our goal, we want to count the number of additions plus, right? In this formula, in this expression, we want to count how many plus signs do we have, right? All right, so here, let me write object 1 plus signs. Okay, number of plus signs, that's object 1. Yeah. But plus sign, it's hard to keep track of it. Okay? Yeah. By looking at the whole formula, how do we keep track of all the plus signs? There is no reference, no good reference. We get lost, right? So that's why it's hard to count directly. Yeah. Now, we try to get to object 2 and one-to-one correspondence. So what's the object 2? All right, so here, right, look at this, A1 coefficient. A1 has a subscript 1. Okay, all right, subscript. So the first plus sign we want to associate with the first subscript. Okay, the second plus sign will associate with A2 subscript. How about that? Okay, we use that. We use the subscript of the next operand, yeah, A2, next operand, subscript, the coefficient, yeah, as the reference. As it's a reference. So here we have a reference, right? Object 2, yeah. And the last plus sign associated with the last subscript, N. All right, so object 2, here we can see we get object 2 subscript. Right? Object 2 subscript. Okay? Is it one-to-one correspondence? Right? One-to-one correspondence? Yeah. Yes. All right. Next, is it easy to count the number of subscripts? Excluding A0, right? A0, the first coefficient, there is no plus sign associated with it, so we ignore it. All right, now you tell me how many subscripts other than the first one, first coefficient. Okay? Yeah, it's obvious because you count 1, 2, all the way through M, and object 2. n number for object 2. That number the same as the number of object 1, the plus sign. Okay? So we get the conclusion. The conclusion is, here we have n additions, and these n additions use n units of time. Yeah. So that's our first step, okay, for additions. Yeah. All right, so next we need to look at the multiplications. In our next video, let's look at the multiplications. Yeah. All right, so let's stop here. Yeah.